life as well as for social welfare for what NIET has always committed. NIET is one of the finest institutions across the country. He served as application manager, additive manufacturing in the field of additive manufacturing in AM division at Additive. Additive is a fact group having its presence in the entire country. Contributed a lot in the field of design and additive manufacturing. Developed various industrial as well as medical applications with additive manufacturing. Also, he contributed to other relevant technologies like reverse engineering, vacuum casting, tool making, etc. Served as an assistant professor since 2010 to 2015 at International Maritime Institute, Greater Noida. Also, Professor Rajkumar, he served as a pipeline engineer in a pipeline project of Trans-Canada Pipeline with Apollos RTD Quality Services. He having the few patent under his name. His highest qualification, Master of Technology in Mechanical Engineering. The person, Rajkumar, Professor Rajkumar, loves to design new products and taking additive manufacturing as a passion. Thank you very much, sir. We got a wonderful speaker, Professor Rajkumar. So I like to share some points about him. Professor Rajkumar currently is serving as an assistant professor in the Department of Mechanical Engineering at Noida Institute of Engineering Technology, Greater Noida, and also be a part of Innovation Lab of NIET and also contributors for innovations to improve social lives as well as for social welfare for
arises in the mind that what is additive manufacturing. So additive manufacturing is also known as rapid manufacturing, also known as rapid prototyping. So if we are talking about the definition, then we can say like process of making a physical object from a three-dimensional digital model is known as additive manufacturing. Typically laying layer by layer, laying layers down many successive thin layers of a material is also known as additive manufacturing. So additive manufacturing is also known as rapid prototyping. There is a story behind it. Actually, this started initially in early 80s with an invention of photopolymerization process. So earlier, the thing which was associated with the technology was only the prototyping. So in earlier days, the prototyping was the main concern with the manufacturing sector. So in those days, prototyping was done with the help of some manual operations like some cutting, like some sectional cutting tools were there, and on the basis of joining them together to form the 3D object. So that 3D object were formed in those days with the manual operations. So with the help of some paper, with the help of some seeds, with the help of some like plastic material, we can say by cutting them manually, by cutting them with the help of some cutters, on the basis of them we created, we used to create all those shapes in order to achieve those prototypes. But soon after just this process was not that perfect in terms of, like, if we are talking about the process of making a component, it was not very much rapid. It was just a slow process. So the prototyping section itself took long time in order to get into some decisions. So if we are doing some prototyping task and we are spending a lot of time on the single approach, which is also known as prototyping, and in those prototyping approaches, we cannot achieve the actual components with that spent of time, and still we were not able to justify that it will work for us. So that was the challenges with the prototyping in early days. Then later on, in early 80s, uh, with the invention of technology known as photopolymerization, which is also known as stereolithography process, with a person named Charles Hull, who is the owner of the world-leading company known as 3D Systems. So he invented this technology, and with the help of this technology, people were able to do the process of prototyping in a rapid manner. So that is why the term converted into rapid prototyping. So time spans on the technology, more technologies comes into the existence. Then strategies develop their own technology, which is known as fuse deposition modeling. So due to this, the technology found more potential into the industries. So that more potential were found, and uh, different manufacturers, different industrialists, they realized that the technology has lot more potential than the prototyping section. So the prototyping was not only the thing which were processed with the help of this technology. So in order to get some more advancement in the technology, there was a lot of research went with different materials, different approaches of depositing of material in layer by layer manner. So all those research approaches, all those R&Ds, get them to form a new concept of manufacturing. So it concept known as additive manufacturing, also known as rapid manufacturing. Some people called it 3D fabrication, some people called it additive fabrication, some people called it layer manufacturing. So these all terms drive through the innovations time to time. So these time to time innovations carried out with the help of different people, set of people who were associated with the technology. They have developed many technology. Nowadays, if you look at the today's scenario, we are having various materials, various technologies which are existing in this particular technology. So at the time past, the thing was that like in earlier days, there was a computer, like we can say a computer system, or you can say some system which we were using initially. In those days, if you recall those days, in those days, the invention of computer took place. So in those days, the computer were not that popular among the people, because it was only utilized by few group of few people who were associated to some analytical problems, some uh, like specific applications, like some war, something like that. So all those applications were addressed with the help of computer. But nowadays, if you look, everybody is having his own personal computer, or you can say a laptop. And today is the cell phone, modern cell phone is a kind of modern computer device. So in the same manner, if you look at this technology, additive manufacturing technology, you will find that the technology is not only associated to few manufacturers, it is not limited up to certain applications, which we can say the prototyping applications, some specific application related to the manufacturing sector, some medical applications. But nowadays, a common person also can able to use this particular technology for their own applications. Like if they are having some customization with their components, if they are having some like variety of design thinking approaches with them, they can use it. If they are having their unique ideas, nowadays if you look at the people are having their own innovations, they can make them reality from the digital file format. Earlier it was not possible. Actually earlier, if you look at those people who were having their brilliant ideas, so those ideas, if you were able, you were not able to transform those ideas into the physical form. So those physical formation is now possible with the help of these technologies. So nowadays, if you look at the technology in the modern era of this technology, you will find the technology is more relevant to those people who are developing, who are innovators, who are individuals. Like nowadays, if you look at the people, everybody is having potential. If he's having his own ideas, he's having the potential to realize all his different, you can say, all his different ideas to turn into reality. So this is how technology is working. So nowadays, if you look at the look around, the technology is known as one another term, which is known as 3D printing. So this is the whole journey which started from rapid prototyping, turned in many innovations, and now it has been generalized. It has been utilized by some certain set of people. It is now utilized by general common people for their making their hobbies in reality. They're like thinking into the reality. They can convert their digital models into the physical models. So this is how it is transformed from its early stage, and now today we know this technology with the common name which is known as 3D printing. So this is all about the brief idea how this evolved from some certain set of like you can say technologies to number of technologies. So here I want to say some differentiation between the, you can say some differentiation between the two which are the most common technologies with us among us. So these two different technologies are, one is considered as the subtractive manufacturing, another is considered as additive manufacturing. So the subtractive manufacturing is more relevant to the tooling side. If you look at this particular image, then you will find if you want to achieve a specific shape, you should have a shape with you that can be transformed with the help of some machining operations. So machining is more involved. So a lot of material can be washed out from the specimen. That specimen can be washed out with the help of some tooling operation. That cutting may be there, like grinding may be there. All those operations can remove the material from the specimen to achieve the specific shape. But the approach with the additive manufacturing is very different. So if you look at the approach which is related to the additive manufacturing is very different, which creates the object by deposition of layers in a predefined thickness. That predefined thickness could be like anything, which would be further dependent on your material, your technology, whatever the technology you are going to use. On the basis of that, you are depositing the layers successively to achieve that specific shape. So there would be some advantages, some limitations would be there. We will be discussing in the further slides. But the approaches will be like, if you are having a specimen, you are taking out the material with the help of specific operation like cutting, shaping, and different operations are there with the machining. Different machining operations, you can say. But here you need not to use any kind of machining operation, where you are having different operations to deposit the material layer by layer. So this is something which is related to the additive manufacturing, which is the most important thing in additive manufacturing. Actually, there are various operations. If you say, like, there are operations started from the design. The basic need to create a 3D object is a design, which is also the necessity for all different manufacturing process. So this is also required here as well. So in this particular process, you are having, one is a pre-process, which is a design phase. Then there is a building process, or you can say some part generation process or transition process as well. And then you will be having some post-processing operations along with the different approaches. So we will be discussing that process chain there, but slicing is the important part here. So here you can see there are three different pictures over here. So one is just to make you understood that the object is like this. This is our object. This you can consider it as like you can say it is a digital model, you can say. So this is a kind of digital model. Here you are doing a slicing. So slicing is just similar like if you are in a potato and you are converting them that potato into the chips. So chips, if you joining them together, then it can give you the appearance of the potato. If your chips are arranged in the right order, like whatever the way you are making chips out of it, but if you are joining them together in the specific order that was initially with the potato. So in the same way, if you are converting that digital model into some fine layers, or you can say some chips form, you can call it a chip. So in the form of chip, you can convert that model into the different layers. So that layers will give you the specific resolution, as well as you can say the layer thickness is there. So that those thicknesses would be that would be vary according to the technology, according to the material. So this will justify about how you can slice the object, and there are very more things also associated with this particular slicing process. There is not only the single operation that you are performing here just to cut it out, but there are various operations to do it. There are various parameters which are associated with this, because there are different technologies, and different technologies are having different materials, and according to different materials and the different way of deposition, all those different depositions will have different set of parameters. So different set of parameters will give you the different approaches of doing it. So that identification is very important. In further slide, you will find how you will be identify all those different shapes, all those different layer thicknesses, all those different your model to be how to achieve a correct model, and how to get that right model into the correct product. So all those things drive through your requirements. So requirements is directly associated to your applications. So your application part is most important. So if we are talking like if we are taking some overview of this thing, then we can say there are three important things. One is your application, which is I think which is the most primary thing which you should consider. First is your application. Then second part is your system, what system you are having with you. But the system, I placed it at the third part, because the most important thing in order to address the application is your design. So design is most necessary thing in all this process. If you are not having the correct design, then your output would not be desired as per your application. So design is the important thing. Most important thing is the design in order to solve your purpose in terms of application. And then your system is there, and according to the system you will be having variety of materials. So those variety of materials and all these things are interrelated, but the basic thing is your design. So design is the most important thing, because machine will do whatever you will command it, command to the machine. Like if you are having a specific machine, you are preparing a set of instructions. Like yesterday we were having a session, they were explaining about the G codes. So G codes are the simple set of instructions. So those set of instructions can be given to the machine. So machine will just follow the instructions. There is only two things. One thing is that the machine could have a hardware which is most accurate hardware, then that can affect the quality of the product. If it is not that great hardware, that in that case you will find some quality compromises. So that is there, but still machine has to follow the all instructions. All instructions can be given by the slicing operation. So that slicing operation is the mediator between the design and your machine. So you can say like this. So that slicing software is having various parameters in various concepts, in various technologies. So here, if you look at this particular window or image, you can say that particular image is related to a you can say FDM software, FDM slicing software. FDM, or you can say your FFF, fused filament fabrication. There are two terms which are associated to the FDM, which are like one is FDM, fused deposition molding, another is fused filament fabrication. So nowadays everybody can use every term, but earlier it was not there because FDM was the patented term. So initially the technology which was associated to this particular thing was termed as fused filament fabrication. So this is one thing. Now you can use any term because a patent can or a copyright can be go up to that is having a specific age. So you can use nowadays any term, whatever you like. So here you can see this is a software or you can say slicer, which is a open source slicer, which is having different parameters. So if you look, if you are able to see all those different parameters, I would pronounce them like some layer height, cell thickness, all those different parameters are there which are associated with the FDM technology. In the same manner, you are having different parameters which are associated with SLA, some parameters which are associated with some other technologies. So there are the different technologies we will be discussing about them, and we will be having some idea about all those different technologies and what are the different parameters which we have to consider while pursuing all those technologies. What are the advantages related to that particular technology? What are the limitations with that particular technology that we will be come across? So this is the broad prospects of that additive manufacturing process chain. So in this particular process, you will find this will explain everything about the process, like everywhere, whatever the thing you are doing with the additive manufacturing, it is present in this particular image. You will find everything here. So it starts with a 3D model. So 3D modeling can be taken place with the help of your CAD softwares. So CAD softwares are also associated with different, you can say, different, you can say categories. There are like some parametric CAD, some you can say artistic CAD softwares are also there. Like there are variety of CADs. Some CADs are associated with some sculpting applications. Some CADs are associated with jewelry based applications. Some are related to architectural applications. And in the same manner, the broader way of using CAD is your parametrics. So there are some CAD softwares like Creo, Unigraphics, or you can say NX software, which is similar to Unigraphics, and then CATIA, SolidWorks. All those softwares are parametric CAD software. Then there are some artistic CAD softwares like you can say Max, Maya. These are known as artistic CAD software, but they all termed as the design softwares. We call them in a generalized term a design software, but there are a lot of difference because we in some softwares we create the part through some specific parametrics like vector geometries. Some parts we create with the out of some mesh structures. So through the mesh we create the components. So there are the different differentiations among the different CAD softwares. Apart from that, we are having a different way of getting 3D model. So one way of getting 3D model is known as 3D scanning, and CT scanning is also one more process. CT scanning is nothing but just to create the volumetric scan. So that is a kind of volumetric scan. So volumetric scan is can be defined as like if you are having a 3D scanning, then in 3D scanning usually you will be capturing all the surfaces of any component. But in volumetric scanning you are also taking the depth of that particular component. Like if you are going through a CT scanning, then your internal bone structure will also be captured. So this is how you will get the counters, or you can say some cross sections of that specific area which you are capturing. So all those are the sources of design, and there are some sort of like if you are making a design out of some parametric CAD softwares, then there will be less chances of some issues in the design. But if you are having some software which are associated to some capturing operations like CT scans, like if you are having 3D scanning, like you can say laser scanning, white light 3D scanning, like a surface scanning, you can say. So there are different operations to do. There are different way of doing 3D scanning, surface 3D scanning. Like there is a process known as photogrammetry. So photogrammetry can give you a great image out of it. So that images, those surface capturing won't give you always the 100% accurate data. And even if you are doing it in CAD software, there will be also some issues in those designs as well. But parametric CAD data will not have that much of issues. And even if you are designing through some artistic softwares, in those cases also, you won't find much difficulties. But if you are having some optical extraction of data, optical extraction means if you are doing some 3D scanning. So in optical extraction of data, you will definitely find some issues, because there are some limitations with the optical extraction in data. So those limitations are like you cannot scan data which is having the reflective surface, which is having the transparent surface, that you cannot capture. Apart from that, the depth which is available on the component, because all the components cannot be as simple as you are thinking. Some components may be some flexible, some complexity would be there. Some components would have some holes inside the body. So in those cases, you would not able to achieve the right data. So that data can be achieved in the form of point cloud data. So that point cloud data can further be converted into the required file format, which is known as mesh file format. So ultimately, our objective is to achieve the right, correct mesh file format. So all the data, all the softwares are having capabilities to export the data in the mesh file format. And the mesh file format is nothing. It is a file format where you are converting the whole surfaces in watertight model. Watertight model is having no issues, and that mesh is having filled the surface with number of triangles. So all those facets repeats itself. So that repetition of facets and putting those triangles over the surface will give you the exact geometry of your STL file. So that STL file can have various issues. That can be done through the transmission, that can be done through the conversion of data from one format to another format. Suppose you have designed something in CATIA. If you are exporting that file format to some different file formats, then there will be some losses. And if you are transferring this to a specific software, different software, then every transmission will have some losses, because if you are capturing an image through your cell phone camera, if you are transferring through some like you can say any kind of platform, like you are transferring it through WhatsApp, some mail or anything, you are transferring the data, there will be some losses in the data. The best format would be the parent format of the file. So if you are extracting in the .cat file, then it will be fine. But if you are exporting it in some other file format, there will be some issues. So all those different issues would be there. So these issues can be rectified by different set of software which comes under the transition phase. So that is the transition, you can say a format of your process. This transition format of your process is having different set of softwares. Also, apart from that, there are some capabilities within the softwares which are associated to the slicing, or there are some softwares which itself are having some capability of exporting the right file format. So there are some inabilities in the softwares. So yesterday we were having session on DFAM. So DFAM is an approach of designing according to your additive manufacturing process. But if you look at the different conventional softwares, you will find those softwares are incapable to produce the shapes which are more associated to your additive manufacturing, because additive manufacturing is a different approach. So there you have to consider, according to the different technology, you have to consider the different parameters which are there. So all those parameters could be some of the process would be having the volumetric building process. If you are working with your you can say some SLS process or something, then you will find that there is an approach of building in volumes. But if you are working with some FDM or some similar technologies like that, you will be able to use only the built platform. You would not able to utilize the whole volume. So there are some different approaches. According to those approaches, your programs, your software related to your designing need some modifications according to them. So all those modifications cannot be possible into the conventional CAD software. So that is why there are different tools, different modules, different softwares which are having the specific capabilities in order to produce the design according to your additive manufacturing. So this is how this will work. So in order to achieve the right model, you have to identify the right software, which is not always like if you are working with some parametric software, then there will be far less issues if you are comparing it with some other process like 3D scanning. So 3D scanning is further having the different approaches of doing it, because 3D scanning will create a lot of data. That data size is bigger than your parametric data size. So if your model is related to your parametric applications, like if your model is more associated to your industrial manufacturing, or you can say automotive or some similar industry, so all those data will be having data will be having capability to regenerate with the process of reverse engineering. So reverse engineering is a process we have to actually your capturing of surfaces or capturing of 3D scanning will give you the overview or the idea of the dimensions. It will not give you the exact geometry. If you are working with some different applications like prosthetics, and you are working with some like sculpturing applications, some medical application, in those cases it would be fine to rectify the same data. But if you are working with some parametric applications, in those cases you have to rectify that data. You cannot even rectify, you have to create a fresh data with taking reference from the point cloud data, or you can say data which has been captured. So this is the process of doing reverse engineering. With the help of this, the whole scene is this: you can create all the data and then you have to convert that into the mesh. Then mesh will be having further issues, some holes, some overlapping, that will take further more time to discuss. So there are some issues you can consider this. Then those issues can be rectified with the help of some you can say third-party softwares are there. Some slicing softwares are capable to do it. There are some powerful slicing softwares. So all those rectification can be done according to your system, according to your requirement, according to your application, according to your material, because every parameter will have some issue with the mesh. If your mesh is being exported, that mesh is imported into a slicing software, then that slicing software will also have power to accept or decline that particular model, because that is having some certain set of instructions within the slicing software. That software gives you that idea whether it is feasible to print on that particular system, on that particular 3D printer, so that you can achieve the appropriate data. That errors would be there, and sometimes some slicing softwares are powerful enough to check them and prepare them accordingly. Let's take an example, like we are having a machine which is having the minimum feature capability of 1 mm. It is something that feature can be produced from the machine. If you are having some component with you, then it can, the minimum capability of producing thickness is 1 mm. If your data, if your design is having 0.5 mm, in those cases what will happen? It will not accept that file, or it will give you an option to enhance that thickness. So this is something which is available in slicing software. So this is how it transferred to the slicing software. So slicing software itself, according to your system, according to your application, according to your material selection, your slicing software is having that capability to accept or reject that file format, or some softwares may not have it. So you have to initially go through some third-party software or go through some like correction process. That correction process will give you the appropriate mesh. That appropriate mesh will be then transferred to your slicing software. Then slicing software slicing it to form instruction file, which is known commonly known as Z code file. That Z code file can further send to your system. So your system could be anything which can belongs to any kind of technology, and according to that technology, your slicer is get programmed, and then that slicing can further send to your post-processing section. Then post-processing could involve various operations which will further dependent on your selected process or selected material. So all those different post-processing operation can be performed, and the majority of post-processing operation would be having some support removal or some surface finishing. All those operations would be there. Let's take an example, like we are having ABS material with us. Then ABS material can have the surface finishing with some chemical treatment by acetone. And in the same manner, if you are having some support structure which can be dissolved, there are some support structure which can be dissolved with the help of some solutions or water. Like PVA is a material which can dissolve into the water. So if the support structure is made from PVA, then you can immerse the whole component into the water. Then water can take that PVA into it. So you will be drained out the support structure. In the same manner, if you are having the support structure made from HIPS, then HIPS can dissolve into D-luminance solution. So these are some like post-processing operations which we can do. Apart from that, there are some heat treatments are also there, some surface grinding are also there, some sanding operations, or you can say support removal with the help of some some tweezers and different tools which are the mechanical process. So these operations are associated to the post-processing. Here then, this is a broader way of different process. So if you look at this particular chart, you must have seen that before as well, but this will give you an idea how the process will work, how it works from scratch. So scratch part is the CAD part, which is obviously a design part. Then design can be further converted into the STL file format. So you must be thinking that if people are aware, then it is great. But if somebody is not aware, then I will mention here one more thing. Like there are some terms like STL is there. So STL is nothing. It is the file format which is associated to the mesh family. So mesh is a file format which is having triangles in it over the surface. While you are having a surface like you are exporting a model in STL file format, it will be converted into the fine triangles. Like number of triangles will be covering it, and the more the number of triangles, it means that more the resolution would be there with the design. If less the number of the triangle, then it is totally dependent on your chord length. So chord length is the side of, or you can say a vertex of your triangle, you can say in layman term, but it will be totally dependent on your number of triangles. Like if your number of triangles is more, then your resolution will be high. It can be understood with the further some slides. I will explain that in further slides as well. So STL is the standard triangulation file format, and which is also known as stereolithography file format, because earlier this file format was only dedicated to a specific technology, which is known as SLA. So SLA was stereolithography, so that is why it was termed as stereolithography file format. But later on, as there are the different name, like standard triangulation is the name, standard tessellation is the name. So these are the name of the same file, and it is the family of mesh, because mesh are having a few more file formats, like PLY is a file format with the mesh, OBJ is also the file format with the mesh. So there are the different file format with the mesh. Then there is a file transfer to machine. File transfer to the machine, then in this particular process, if your STL file is get converted, then that file cannot directly send to the machine because machine won't understand that language. Machine will be run over some program. That program can be generated with the help of your slicing software. So the slicing software can convert your STL file into the G code. So G codes are nothing but these are some set of instructions according to your machine. Then there are some machine setup as well. So you have to set up machine accordingly, like there are some calibration operations, there are some, it depends on your different technologies. Like if you are having SLS, then you have to prepare the build, you have to fill some powder based material. If you are having SLA, which is liquid based technology, where you have to fill the resin. In FDM process, you have to calibrate the machine, you have to set up some temperature with the bed, with the nozzle. These are some operations associated to the machine setup. Then there is a building operation. Building operation is nothing but to allow the machine to follow the instructions which were produced with the help of G code. Then it will be the building operation. Then removal of component. While you are building a component, you are having different technologies, and according to the technologies, you are having the different process of removal of material. Like in some metal cases, like SLS is the process. In SLS process, you are having a process of wire cutting of for removal of component from the machine, and in powder based like polymer process, you are having process of with the help of taking out the material with the help of some vacuum apparatus, or in FDM process you are having scraper with you. So there are the different process of removal of component from the machine. Then there are some post-processing operation. I have already explained to you that post-processing operation further dependent on your requirements, further dependent on your material uses, for what material you are going to use. So this will be dependent on that. Then the application, whatever the component, the objective of creating the component, that application can be solved. But nowadays, if you look at the application part, then you will find there are more than 75% of components are produced for prototyping purpose only. There are no further purpose. If you are looking at the broader prospect, you will find more than 75% components are prototypes. The real-time applications are very few. This is something which will explain you about like what is the CAD model, what is the mesh file format or the STL file format. So if you look at the left image, you can say it is a CAD model, and if you look at the right side image, you will find it is a mesh file format, or you can say STL file format. So here you can clearly see there are number of triangles which are here on the surface of that cup, and if you look at this particular part, this is thinner than this whole component. So you will find there are the number of triangles will be or you can say the density of the triangle is visible more. But if you look at the broader prospect of this whole image, this will be having the equal resolution. If the triangle size at this particular section would be similar to this surface, then there will be some you will be having issues in this particular area of this component. So those issues will be associated to your resolution. So in order to do the resolution, so triangles distribution is not dependent on your size of triangle. It will be dependent on your resolution. This portion you can see, this portion is again associated to the specific application. So if you are having a single like square or a rectangle surface, then you will find only two triangles over there if it is having a plane surface. But if it is not a plane surface, accordingly the distribution of triangle will take place according to the resolution. So resolution is the important thing here. So the resolution would not compromise. So that resolution will be totally dependent on this chord. So chord is there. So that chord will be varying according to your surface features. So it will be distributed according to your geometry. So this is how it will take care. A software can take care to export the file. So how it will affect the geometry if you are not working right way with the resolution. If it is with the that particular, you can say this particular object will explain this in a very clear way. Like if you are not giving the right resolution in this particular component, then you will have some issues with this resolution. So that is why it is clear at the design phase. But if you are working with your process, like if you are doing with the printing or the your additive manufacturing system, then in those cases you will find these effects in this while deposition. If you are depositing the layers, then you will find some staircase effect over here, which is minimum here, because here the layer thickness of the component is less. The thickness is very less, so the resolution is high. So this is how you can identify at what particular surface what kind of layer thickness should be there. So there are three main pillars so far we can say. So the three main pillars are design, and second is printing, and third is post processing. So in design, you are having we were discussing about DFAM, design for additive manufacturing. So in order to use the additive manufacturing process, you should have some design specific rules, additive manufacturing specific rules with us, so that those additive manufacturing specific rules can give you the idea. Like those rules need to identify, like we are generating a geometry which is similar to a Taj Mahal structure. So the Taj Mahal structure will be having a dome on the top, and there is a conical shape on the topmost part of that dome, and there is a plain wall over there. So in additive manufacturing design rules, what will you do? You can, in order to optimize the time, if you are going to optimize the time, then what will you do? You will give more layer thickness to the plane region in order to compromise the time, but that plane surface won't compromise the resolution, right? So that compromisation would not be there with the plane surface. So that plane surface will be having that specific layer height. That layer height can be given as max as you can with the existing system, but with the dome shape. Like earlier, we have seen this particular structure. This particular structure is having this special geometry, and this is the universal geometry of this cup. So that universal geometry is having a specific size of your triangles, but here the triangle size is different. In the same manner, if you are slicing it for the Taj Mahal will be having a dome shape over there, and the top of that Taj Mahal will be having a conical shape, and rest of the part will be having a uh, plane surface. That plane surface can be deposited in z-axis. So if that plane surface, if this is a curvature surface, this is a plane surface, that plane surface can have the higher resolution, lower resolution, but that surface should have the higher resolution. It means that the layer thickness at this particular section should be higher, lower, and at this particular section should be higher. In that way, you will save some time in order to build the component. So this is how we will do additive manufacturing specific design rules we can implement on doing the process. Then the softwares are also very important because software itself are having capabilities to accept those designs according to our requirement, according to our application, according to our system. Softwares has that potential. So these are the design rules which we follow. So design will consider that rules, and the software together will give you a design related approach. Then further process is related to your system. Your system will be having three further things. One is your hardware, which is with you, that is known as system. Second is material, and third is post process parameters. So it is just similar to your computer, like computer is having some software with you, like operating system in terms of material, and process parameter in terms of your process, whatever the process you are doing with your system. So like you are playing game, according to the game you will be choose your processor. So in the same manner, your system is there. System is like whatever the system you are using, it is SLA, SLM, or EBM, MJF. FDM, whatever the system you want to choose, that will be further dependent on your application. And material, whatever the material is, uh, uh, a machine could capable to print in what material. Like if I would say ki I am having a FDM machine and I want to print with titanium, would it be possible? It will not. So these all three things would be dependent on your applications. Like your application is related to a biomedical, and in those cases you should have a biocompatible material with you. So you will choose the biocompatible material, then you will accordingly choose the system which can having the capability to operate the biocompatible material, and accordingly the process parameter will be set. So all three things will be interdependent. Like if I am having a flexible material, that flexible material cannot be uh, print on a specific system. That system, like if we are talking about the like FDM technology, in FDM technology there are two type of drives. One drive is related to board and tube drive, another is direct drive. It has found that the direct drive is more suitable for flexible material than board and tube drive, because board and tube drive is not capable to extrude the material in right proportion. That is why we can use only the direct drive system with us, and the material will be the flexible, and the parameters will be bit different than the rigid material, because the flexible material would not run with the retraction settings. So those settings that we will be changing is more associated to the process parameters. So this is how these three things works together to make a successful print. So these three operations will be there, and according to our requirement, according to our applications, these can be suffered. Then after that, we are having another pillar with us, which is further associated to your application, your resolution, your appearances, because I have mentioned that 75% plus are for the prototyping purpose. So if you are having 75% plus in prototyping section, the main objective of doing prototyping is that to give you the feel of the object, like appearances of the object and the form and fit check. If you are going it and doing it, the form and fit check and the appearance, you will be requiring the surface engineering or the heat treatment. These can be into the post processing part, because surface engineering is something where you are doing some mechanical operations like grinding, like you are doing some process which are associated to your chemicals, like I have mentioned with ABS to acetone, HIPS to delaminin, PVA to your water. So in the same manner, heat treatment is also there. So these are also associated to your applications, like somewhere we are in applications to deliver some specific strength, mechanical strength. If you are talking about strength, it means that mechanical strength. If you are talking about mechanical strength, it means that it should be withstand at particular force, or you can say some particular stress. So it should withstand at that. So the ugly truth with the additive manufacturing process is that in most of the process, you won't find the homogeneous strength. And what is homogeneous strength? It is like if you are building a component in FDM technology, it will be having three axes. One is X, another is Y, and third is Z. The material will be depositing in Z direction. XY will be operational with the build platform. So in that particular case, what will happen? Your XY axis will have enough strength. If you are comparing it with the Z axis, then you will find it is not there. It is 40% reduced, because the joining operation of successive layer will not fuse the layers together in that level. In order to do that, we can have some heat treatment operations with us, and there are few more operations, and there are some practices we can do as per our applications. There are some practical practices as well to improve the Z strength. There are some various research papers are also available related to it. People are working on it in order to achieve the homogeneous strength, and there are various technologies as well which are available to give you the either near to the homogeneous strength or the exact homogeneous strength in Z axis and the different axes. So there are some technologies like we can name them, like SLA is one where we can get the homogeneous strength, but that's the another part that we can even not get the mechanically strong part with the SLA technology, but whatever the strength we achieve with the SLA technology is uniform throughout. So it means that it is a homogeneous in strength. So this is how we can work with all these three pillars of process chain. So these process chain will have design, printing, and post processing. All three things together will give you a successful component. So there is another thing which is associated to modeling, which I believe I have already explained. Like there are some softwares which are associated to some parametrics, some are associated with your uh, artistic, some are associated with your 3D scanning operations. So with the help of 3D scanning, you can do the scan. And alternatively, one more process I hope I have explained, but I have missed few points out of it. So there is a process known as your your process is known as CT scan. So CT scan is a volumetric scan kind of process. So in CT scan, what will happen? Like here, it will capture only the surfaces of that particular object. But in CT scan, what it will do? It will scan the surface by volume in layer by layer. You can set up those number of counters with the CT scan machine, then it will capture the whole surfaces layer by layer. In that way, you will have the internal parts as well. That parts can further be exported into a DICOM file image. That DICOM file is a medical file format that can further be converted into STL file format. In that way, you can also achieve in 3D printing, mostly you will be getting the outer surfaces of the component. Rest of you can control according to the technologies, like whether you want to fill it with 100% material or you want to partially fill it. That will be further dependent on the technologies. So in that particular process, in CT scan operations, that data will give you the STL file format that can also enable you to print with the internal features. So those internal features can also be print. So this is how CT scanning data will work. So there are some advantages with the technology. There are some advantages related to technology are that complex shapes we can create, freedom for design is there, customization part. We will show you some examples so that you will be able to understand what these different points will state. So these are some complex shapes which you cannot create with the help of some conventional process. You can create with the help of additive manufacturing process, because these are very complex shapes, and even these complex shapes can be designed with some artistic softwares. You cannot create those designs with some normal, you can say, parametric softwares. So if you are going to create those shapes with conventional process, either it is not possible or you have to take lot of like tooling operations need to incorporate. These are some examples related to freedom of design. You can do it like in fashion industry, whatever the shape. Like sometimes what will happen, you want some product to be built and that product is not available in the market, but you want something like, you can have some feeling like that if this kind of product could be there, then I would be do my this stuff like in that way. In in this uh, in this particular approach, you can go with additive manufacturing approach. You can, whatever you are thinking now, by the next day uh, you will be turn it into reality. Like whatever the application you are thinking in your mind now, you can be convert that very soon. The process is not very like slow nowadays, it is very fast nowadays. If you look at the market, you will find that nowadays you will see a single segment of a particular automobile industry will have lot of different you can say, if a company is driving two segments of a car, then a single segment will be having number of cars uh, in his you can say portfolio. These are some customized parts. Customization could be there, that customization according to your requirements, so which was not possible earlier. with the help of this technology, and obviously with the help of design, because I have mentioned it that design is the most important thing in all this process. So design is the primary thing and the basic thing. On the basis of design implementations and the capabilities related to the technology, you could able to create the customized parts, and those customized parts could be even better than the actual components, if you are comparing with the natural leg or the limb of individual. Then less waste. If you are like here is the example, like you are having this particular material with you, the raw material, and you are going to machining it and you can create that product, then this much of waste you will get. If you are doing the same shape with the additive manufacturing process, then this much of material will be consumed and this is your final output. This would be the waste out of it. So initially consumption of the material will be less, and after that your final output will have a very limited amount of waste. Fewer unsold products. So this is an example of fewer unsold products. Like nowadays, if you look at this particular car, there are few owners, but there are no spares available. No company has been closed. So in order to get those spares, in order to do that, you can pursue this particular technology. And there are a lot of products which are discontinued in the market, but they are still having their owners who are suffering for deficiency of those components. So those components can be created with the help of such technologies with a reasonable prices. So that can be created. Less transport. Here I would mention one thing. If you are like having a car, your car is having a spare wheel with you. For worst scenario, you are carrying a spare wheel and some tools with you like jack and all those stuff with you, spanner and all. So those stuff is with you for your safety purpose, like you are driving on the road. And road can have like if you are driving on the road, so you will hardly 10 or 15 kilometers far from a repairing shop. But if you are traveling in the ship, if you are traveling in the spaceship, then in those cases there is a difficulty of carrying the spares. If you are carrying only a single spare with you, then it will not solve your purpose. You have to carry a great inventory. So all those inventory you have to carry. So in order to reduce that cost or that like if you are carrying inventory, it will obviously fill some spaces and also make effect on the overall weight of that particular spaceship or the ship. So in order to reduce that, you can, instead of taking those spares with you, you can take the soft file or the design of those spares with you, and you can keep a printer or the 3D printer, you can say 3D printer you can keep on the deck or your spaceship, and whenever you will be requiring a specific component or the specific part, you can immediately print with the help of that design. So this is how you can help those applications with the help of 3D printing. So this will help to reduce the transportation of those spares with you, where you are not sure whether you will be requiring it or not. Carrying a spare wheel is another thing, but carrying the whole inventory of a specific vehicle is very difficult. You cannot carry a engine with you, a clutch plate with you in the car. In the same way, you are carrying different spares with you while you are going in ship or the spaceship. So that can be addressed with the help of additive manufacturing process. So this is the design part. Here you will be clearly see how the different number of triangles will affect the different your resolution. So if you look at this particular sphere, the whole all the 6 spheres are having the same radius, or you can say the same surface area or the same volume. But the change in all these spheres are these, that the resolution of this particular left sphere is less and the resolution of this particular thing is little bit higher, and this is the highest resolution spherical part. So this is having a tolerances of 0.1 tolerance. So 0.1 is something which is directly associated to your chord length. So uh, this tolerance will give you the 240 triangle with the specific sphere size. And if you are increasing the tolerance 10 times, then you will find the 2400 triangles would be there. If you are increasing it 100 times, then it will be 24,000 triangles. So in this particular case, you will find very less resolution in the output. Here you are a little bit improved, but it is again whether it is suits your application or not, and then it is the finest part. So this can be the optimized way of doing it. This can be the very heavy for handling to your system or the device, but this can be the optimized one. But this won't be acceptable at any level because this is having very less resolution, and this resolution is not giving the impression of sphere. This is something else. Here is a case study related to the conventional design. The conventional design, if we are transferring, it is more onto the DFAM favor. So if you are having a conventional manufacturing process, then you will be having a conventional design. This is a pedal of a cycle. If you are transferring the same design to the additive manufacturing process, you will find lot of support structure over here. So that support structure is further having some wastage. You can do some modifications on the component in order to reduce the support structure. So you did some modifications over the component. So that modifications further increases the weight of your brake pad. Bike pedal. So that bike pedal has increased its weight, but almost remove the support structure except this. You can further deal with some orientation. Like we are having capability to do play with orientations. So you can orient the component in the specific, like earlier we were printing it in the flat format, but now we have oriented it. And then further some modifications almost with some reasonable amount of like weight increment. That weight is not harming much, but it is a reasonable weight which we have increased, but we have reduced the support structure at this point in time. But still, it is a conventional process, and we have to increase some weight over here, and we have switched to additive manufacturing process. But why cannot we use design like this? Because this kind of design is not very feasible with the conventional process, because it will increase your efforts on the conventional process. But in additive manufacturing process, there is not such limitations. You can create designs like this, not even this, but you can create all those different designs, which are very much like attractive than the previous one. And you can create them without creating a support structure. You are having all your choices. So this is how TFAM, along with your additive manufacturing process, you can uh, improvise different designs which are already exist in your conventional additive manufacturing process. This is another example. So this is a aircraft seat belt, so which may be in steel, which may be in aluminum. If it is in steel, it would be in 155 gram. If it is in 120, then it will be aluminum. It will be made with aluminum. So with the seat belt, if you count those seat belts in a aerospace or aircraft, if you count them, then in aircraft you will find there are number of seats. Like if you are consider the smaller one, then there will be like 32 rows and 6 columns. And if you are going with the major one, then there will be 16 columns and there will be like 150, 180 rows. So there will be a lot of seat belts in the aircraft. But if you are going with additive manufacturing process, but this design, if you are going to do with conventional process, it will have lot of process in it. Your effort will increase. But if you are doing it with the additive manufacturing process, then your material will reduce. No any kind of strength compromisation, nothing, and you will save 68 gram. on every seat belt buckle. These are some applications associated to additive manufacturing, automotive, marine, aerospace, medical, dental, prosthetic, engineering, architecture, and many more. These are some popular applications. There are many more applications. There are the food industries as well. There are you can say some tissue culture industry. There are some in medical industry also. There are some subcategories, and aerospace are also have some categories. So there are the different industries. You can find it everywhere. So this is one technology which is related to liquid-based additive manufacturing system. In liquid-based additive manufacturing, you are having stereolithography process, which is also known as wet polymerization process. I will explain only the principle. The working, as we are running out of time, the working we cannot discuss at this moment. But I am explaining the principle here. The tank is filled with the liquid polymer. That liquid polymer is in the form of monomer. So liquid polymer is nothing. It is a resin which is a monomer, and that can be with the help of a UV light source that can be cured, and that curing will further turn that particular monomer into polymer. Then that process is known as polymerization process. So that photopolymerization process is having a light source which is a catalyst actually for the monomer, and that monomer can be converted into polymer, and that polymerization will give you a solid shape. That solid shape can be created layer by layer. In this way your product get produced. So this is the principle of working with stereolithography, and these are the different components. Then there is a material jetting process. Material jetting process again can have your monomers with you, that resin material with you. That resin material can be deposited, and your head can have some fusing lamp. That light could be a UV light. With the help of that it can set. Apart from that, you can have some different material, slurry material, that can be deposited. With the help of heater or the blower, that can be set. So this is how this will work. This is the mixture of your FDM technology and the SLA technology. Or you can say there is a spray which gives you the impression of the FDM technology. And this is SLS process, where the sintering process is being carried out. So with the help of a roller, we deposit the material at a specific layer height. That specific layer height will give you uh, the layer resolution of the component. And the beauty of with this technology is that in polymers you would not require to create the support structure. So the support structure will be compensate with the help of this powder material. So powder material will allow you to give that support to those overhangs. So this is the beauty with the technology. This is the binder jetting process. This is similar to your SLS process, selective laser sintering process. So in selective laser sintering process, there was a laser. So laser was sintering the material in order to bind the powder form material, and that technology can use polymers as well as metal. And with this particular process, you are having a binder in order to join the powder form material. So this can be used indirect for creating the indirect metal components. This can use for this. And this can also create some components out of some POP material and multicolor materials as well. So there is a simple principle: the binder binds the layers of the powder material, and in this way your product get formed. This is a laminated object manufacturing, comes under the category of solid based additive manufacturing system, in which a roll of paper or a film, and it is also there with the ultrasonic consolidation in metal. But in consolidation method, there is a welding process involved and machining operation involved. But here the roll, this is the fresh roll of your material, and this is the consumed roll. The consumed roll, with the help of a laser or some cutter, it cuts the specific counters of layers. Then layer by layer deposition occurs with the help of this heated roller. So in this way your component get formed, and these all materials can taken out after the completion of component, and then we will get the actual shape of the component. So This is actually we can say additive in one term, but in another term it can also be termed as subtractive manufacturing, because there is a lot of material which is waste over here. So in that way we can say it subtractive as well. But as we are depositing layers, so by that particular definition we can call it additive manufacturing process. This is the FDM technology, which is the most common and mostly most accessible technology with the individuals. So here the this wire form filament material is there, which is fed with the help of a controlled gear and roller mechanism. That controlled gear and roller mechanism is having a stepper motor, and with the help of melting at the end point, this is known as hot end, which is associated to your feeder. This unit is known as feeder. This whole apparatus is known as extrusion assembly. So that extrusion assembly extrudes the material in molten form. That molten form material is deposited with the help of a fine nozzle. That nozzle could be made up of brass, made up of SS. The material dependent on the material which we are using, like we are using PLA, ABS, and in those cases we can use brass. For high-end engineering materials we can use SS nozzle, so that deposition can happen. Apart from that, we can have multiple nozzles as well here, so the deposition takes place with the help of extrusion process. So this is how it will work with FFF process, fused filament fabrication. These are some examples of design for additive manufacturing process. So in design for additive manufacturing process, you will be optimizing the data, optimizing the process, because now in order to achieve those shapes, you need not to do some extra process. You will be creating it in the single go. So if you are doing it with the conventional approach, then in those cases, you will be creating different cavities with the help of tooling operation. That will take further time, and also that will have some further cost over the component. So these are some examples of TFAM approach. So these are some industries in additive manufacturing. These are the direct uses, like you can see here. This is the component in which we can do directly injection molding process. So this is a die. This is the direct use of titanium material can be implanted into the skull. So this is an example of that. This is the direct use in terms of fixture. That can be the welding fixture, that can be the assembly fixture, that can be the machining fixture. So this is the example of fixture. So that can be the direct use of the additive manufacturing process, because the precision is there. And due to the precision, we can also do the gauge. We can create the gauge out of technology. So gauge can be done in order to measure the dimensions of the component produced with the production unit. And these are some indirect uses. We can create the master out of the technology, and with the help of master we can create a silicon mold, and that silicon mold could be done with the help of vacuum casting process. And there, if we are not using a vacuum casting process, we can directly use by using the silicon liquid, and we can create the like out of the master we can create the cavity. That cavity can be created with the help of different uh, polyurethane material. We can fill that cavity, and then we can create number of components. It is very good for small production, small batch production kind of stuff. So this is very much great application. This is a jewelry kind of application where we can use the investment casting approach. We can create the master out of wax, and that wax can be drained out by two ways. Like one way is to center the uh, uh, that particular POP mold, and you can drain out the material. And another way is to pour the molten material liquid, and then it will vaporize. So there are two type of material. One is 0% residual material, and one is that material that can be drained out by the sintering operation. This is another process where we can create the impressions for carbon fiber or the glass fiber fabric. Then it can be take impression. There is another approach to do. We can create this component with the help of dissolvable material, that can be PVA or HIPS, and we can take the impression. We can that is more suitable for complex application. This is quite simple. We can take it out, but if we are not able to take out the component out of this particular structure, then we can use that lost pattern So that lost pattern can be drained out in the water or the solution, prescribed solution. Thank you so much. So now moving forward for the question, if anybody has the question, I am just going on to this particular question section.
Thank you, sir. Professor Rajkumar, sir. We got one question from there is no name. What is the resolution? He asked, what is resolution? His name not displayed, anonymous it came. Hello.
Yes, you're audible, sir.
Yes, sir. One participant sent the question, what is resolution?
Okay, resolution is something like you are having a megapixel camera. So in megapixel camera, you are having like concept of PPI, pixel per inch. So this concept is stated like 1 inch square is having that much of pixel, like 12 megapixel means 12 into 10 to the power 6 pixels are there in per inch square. In the same manner, if you are creating layers, like if you are slicing a component, that slicing of component will creating different layers. Those different layers will give you the exact appearance of that component. That exact appearance of the component will give you the resolution. So that resolution is appropriate your appearance of your component, which will be delivered with the help of your capabilities of material, capabilities of your system. So resolution is a term which is more associated to your appearances. Sir, your mic might be mute. Your voice is not audible.
Thank you, sir. Thank you for your reply. We got a wonderful session, a detailed session about